In previous videos, we have discussed linear independence of vectors. Now I would like to discuss linear independence of functions. Recall that vectors are said to be linearly independent if, when you sum the vectors and set it equal to 0, the only way for that to be satisfied is if the coefficients of each of those summands is themselves 0. That is, there's no way for one of the vectors to be written as a linear combination of the rest. We have the same criterion for functions. We say a set of n functions f sub 1 to f sub n, and here for simplicity of the discussion we'll take the functions to only depend on one variable. All of this can be easily generalized to any number of variables. And let all these functions be smooth in the sense that they are infinitely differentiable and the derivatives are continuous also. Then these functions are said to be linearly independent if and only if the equation if this equation equal to 0, as the only possible solution for this is all the k's are 0. Said another way, let's try to find out the criterion for linear dependence. So I'm going to try to find the condition for linear dependence. Linear dependence means all of these ki's are not 0. So the solution is at least a unique solution for this. The way we're going to find that solution is to take the first derivative of this equation. When you do that, you will see that you don't have any derivatives with respect to k, just with respect to f's. Then the second time you do this, I get that. And I keep doing this n times. You can keep doing this more than n times, but it won't get you anywhere. So nth derivative is indicated by the parenthesis like that. Actually, let me just go n minus 1. Even the nth one is not necessary. So you take the derivative up to n minus 1. Let's try to examine this in the matrix notation. In the matrix notation, the system of equations can be written as follows. I can write it like this: f1 up to fn, f1 prime, and so on up to f1n minus 1, f1n, fn n minus 1. So that's an n by n matrix times k1 up to k1, k2 up to kn is equal to the 0 column vector. Now by Cramer's rule, you can solve for k's. Remember, the Cramer's rule is determinant of this. So let me just indicate briefly what Cramer's rule is. So to form Cramer's rule, let me make an abbreviation of this. Let me call this f1 vector. F1 vector is the entire column vector here, all the way up to fn vector times k vector equals the 0 vector. So that's the abbreviation I'm doing of the above sentence. So the ki, the ith k, is got by taking the determinant of f1 all the way, omitting the fith term, and the omission is indicated by the caret, fn, and in place of the omission you put the 0. So you put 0 in its place, divided by the determinant of f1 without any omission, fn. Now the determinant of the numerator is certainly 0 because one entire column is 0. You're taking the coefficient, the right hand side is the coefficient column. You're taking that and replacing one of the fi vector with a 0 vector. So you are going to get a 0 determinant on the top. But that would mean ki is 0. We need non-zero ki for linear dependence. The only way to salvage the situation is by demanding that the denominator also be 0. So the important condition for linear dependence, LD, requires that the following quantity, known as the Wronskian, which is the determinant of, now I'll write it out in full, is 0. Said another way, if this condition is not satisfied, then the functions are linearly independent. So the functions are linearly independent if and only if the Wronskian is not 0. Wronskian was named after the Polish mathematician Wronski. All right, now that we have this condition, let's take a small example to figure out how to use this. Suppose I have a collection of functions where fi is equal to x to the I. So I'm just completely making this up. And let's say I equals 1, 2, 3. I want to keep this manageable. So it's just a 3 by 3 Wronskian. So let's find out so let me write the functions down. The function is going to be x squared, x cubed. Now, at first blush, you can't really think of any way these things can be thought of as independent of each other, because these are not vectors. These are more like functions. But these functions are elements of the vector space of all functions. So at a higher level, when you talk about functional analysis, these are actually legitimate vectors in their own right. So functions are vectors in the appropriate place called the space of all functions, or the function space. So anyway, that's for another day. But right now we'll just focus on the computational aspects of this problem. To figure out if they're linearly dependent or not, form the Wronskian. The first row of the Wronskian is just to put the functions without any change. Then you take the first derivative, and then you take the second derivative. There you have it. It's most convenient to expand this Wronskian from the bottom because there's a 0 there, and that's usually the case for Wronskians. So I'll use a sign assignment for the cofactors. It's actually plus minus plus. The way it goes is plus minus plus minus plus minus plus minus plus. It's -1 to the row plus column number, row number plus column number, if you want to do it like that. So once you have this, you can do the computation. It's -2 times x times 3x squared, which is 3x cubed, minus x cubed, plus 6x times x times 2x, which is 2x squared, minus x squared times 1, which is x squared. So we have -4x cubed plus, so that's x squared, which means that it's going to be plus 6x cubed. And so that quantity is 2x cubed, which is not 0. So the way you write this is you say it's not identically equal to 0. You put a triple equals sign. You don't put a double equals sign and put a slash through it, because it is equal to double equals 0 at x equals 0. So you need to put a triple equals sign. Triple equals means identically 0. Identically 0 means it's 0 irrespective of the input of certain specific values into the identity. It is 0 no matter what. So this is not identically 0, because unless x is equal to 0, it won't be 0. For other values of x, it is not 0. So away from the origin, this is actually not 0. So that's why you put a triple equal sign and then put that not equal to 0. For all x belongs to r minus the origin. So away from the origin, there is linear independence of these functions. At the origin, of course, these functions are 0, 0, 0, so it's not linearly independent. But there is a concept, and this probably takes you a little bit to more advanced realms, but there's a concept called the measure of a function. It is used in a sense of is there any place for us to integrate? So there is certainly a place for us to integrate away from the origin, the whole range of solidity in this thing. So this Wronskian, the functions are, we can say the functions fi are linearly independent except on a set of measure 0. A set of measure 0 is a set which contains isolated points. So if you have isolated points, suppose I had 2x squared minus x cubed, then it would also not be satisfied at x equals something other than 0. So that's also another isolated point. So those are called sets of measure 0. As long as it's not a continuous interval, you're fine. And so the functions are linearly independent. So that's the concept of linearly independent functions, and it's a very useful concept. It can be used in solving ordinary differential equations, as we'll do in the next video, or in future videos in setting up Gram-Schmidt orthonormalization process and to expand various things like Fourier series can be expanded in polynomial bases, and you can expand all kinds of things in weird kinds of bases, and this is the heart and soul behind those kinds of expansions.